Direct from distant planet, spectral clues to puzzling paradox. C Tau b is a paradoxical planet, but new research about its mass, brightness and the carbon monoxide in its atmosphere is starting to answer questions about how a planet so large could have formed around a star that's only 2 million years old. At today's meeting of the American Astronomical Society, astronomers Christopher Johns Kroll of Rice University and Lisa Prato of Lowell Observatory presented findings from a 4-year near-infrared spectroscopic analysis of light from C Tau b, a close-orbiting giant exoplanet, or hot Jupiter, in a 9-day orbit around its parent star about 450 light-years from Earth in the constellation Taurus. The exciting thing is that we are able to detect light directly from the planet, and it's the first time that's been done for a close-in planet around a star this young, said Johns Kroll, professor of physics and astronomy and co-author of a study that's slated for publication in AAS's Astrophysical Journal Letters. The most valuable way to learn how planets form is to study planets, like C Tau b, that are either still forming or have just formed. For decades, most astronomers believed giant planets like Jupiter and Saturn formed far from their stars over periods of 10 million years or more. But the discovery of dozens of hot Jupiters led to new theoretical models that describe how such planets might form. Johns Kroll said C Tau b's age made it the perfect candidate for observation with the Immersion Grating Infrared Spectrograph (IGRINS), a unique, high-resolution instrument that was used during observations of C Tau b from McDonald Observatory's 2.7-meter Harlan J. Smith Telescope and Lowell Observatory's 4.3-meter Discovery Channel Telescope. Because each atomic element and molecule in a star emits light from a unique set of wavelengths, astronomers can look for specific signatures, or spectral lines, to see if an element is present in a distant star or planets. Spectral lines can also reveal the temperature and density of a star and how fast it's moving. Prato said the research team used the spectral lines from carbon monoxide to distinguish the light emitted by the planet from the light emitted by the nearby star. Many of the spectral lines that are in the planet are also in the star, Prato said. If both the planet and star were stationary, their spectral lines would all blend together, and we wouldn't be able to tell what was from the star and what was from the planet. But because the planet rapidly orbits the star, its lines shift back and forth dramatically. We can subtract out the star's lines and see only the lines from the planet. And from those, we can determine how bright the planet is, relative to the star, which tells us something about how it formed. That's because the brightness of a star or planet depends upon both its size and temperature. Direct observational evidence of the mass and brightness of C Tau b is particularly useful because we also know it orbits a very young star, said Rice PhD student Laura Flagg, the lead author of the forthcoming study. Most of the hot Jupiters we've found are orbiting middle-aged stars. C Tau's age gives a tight constraint for putting models to the test. Can they produce a planet this bright and this massive in so little time? Flagg's analysis of spectral lines from carbon monoxide showed that C Tau b has a mass of 11.6 Jupiters and is about 134 times fainter than its parent star. Prato said that provides strong evidence that it formed via a hot start, a theoretical model that describes how gravitational instabilities could form giant planets more rapidly than traditional models. Prato said the new study provides a unique empirical yardstick by which to measure competing theories. At about 2 million years old, C Tau b is by far the youngest hot Jupiter directly detected, she said. We now have a mass and brightness for it, the only directly measured mass and brightness for a young hot Jupiter, and that provides very strong tests for planet formation models. IGRINS, which was designed by study co-author Daniel Jaffe of the University of Texas at Austin, uses a silicon-based diffraction grating to improve both the resolution and number of near-infrared spectral bands that can be observed from distant objects like C Tau b and its parent star. IGRINS was moved from McDonald to Lowell midway through the study. Additional co-authors include Larissa Nofi and Joe Lama of Lowell Observatory, and Kendall Sullivan and Gregory Mace of both UT Austin and its McDonald Observatory. The research was supported by Rice, the National Science Foundation AST 1461918, AST 1229522 and AST 1702267, UT Austin, the Korea Astronomy and Space Science Institute, NASA 18XRP18_20138, and Lowell Observatory. Cool halo gas caught spinning like galactic disks. A group of astronomers led by Crystal Martin and Stephanie Ho of the University of California, Santa Barbara, has discovered a dizzying cosmic choreography among typical star-forming galaxies. Their cool halo gas appears to be in step with the galactic disks, spinning in the same direction. The researchers used W.M. Keck Observatory to obtain the first-ever direct observational evidence showing that corotating halo gas is not only possible, but common. Their findings suggest that the whirling gas halo will eventually spiral in towards the disk. This is a major breakthrough in understanding how galactic disks grow, said Martin, professor of physics at UC Santa Barbara and lead author of the study. Galaxies are surrounded by massive reservoirs of gas that extend far beyond the visible portions of galaxies. Until now, it has remained a mystery how exactly this material is transported to galactic disks where it can fuel the next generation of star formation. The study is published in today's issue of the Astrophysical Journal and shows the combined results of 50 standard star-forming galaxies taken over a period of several years. Nearly a decade ago, theoretical models predicted that the angular momentum of the spinning cool halo gas partially offsets the gravitational force pulling it towards the galaxy, thereby slowing down the gas accretion rate and lengthening the period of disk growth. The team's results confirm this theory, which show that the angular momentum of the halo gas is high enough to slow down the infall rate but not so high as to shut down feeding the galactic disk entirely. The astronomers first obtained spectra of bright quasars behind star-forming galaxies to detect the invisible halo gas by its absorption line signature in the quasar spectra. Next, the researchers used Keck Observatory's Laser Guide Star Adaptive Optics (LGSAO) system and near-infrared camera (NIRC-2) on the Keck 2 telescope, along with Hubble Space Telescope's Wide Field Camera 3 (WFC-3), to obtain high-resolution images of the galaxies. What sets this work apart from previous studies is that our team also used the quasar as a reference star for Keck's Laser Guide Star AO system, said co-author Ho, a physics graduate student at UC Santa Barbara. This method removed the blurring caused by the atmosphere and produced the detailed images we needed to resolve the galactic disks and geometrically determine the orientation of the galactic disks in three-dimensional space. The team then measured the Doppler shifts of the gas clouds using the Low-Resolution Imaging Spectrometer (LRIS) at Keck Observatory, as well as obtaining spectra from Apache Point Observatory. This enabled the researchers to determine what direction the gas is spinning and how fast. The data proved that the gas is rotating in the same direction as the galaxy, and the angular momentum of the gas is not stronger than the force of gravity, meaning the gas will spiral into the galactic disk. Just as ice skaters build up momentum and spin when they bring their arms inward, the halo gas is likely spinning today because it was once at much larger distances where it was deposited by galactic winds, stripped from satellite galaxies, or directed toward the galaxy by a cosmic filament, said Martin. The next step for Martin and her team is to measure the rate at which the halo gas is being pulled into the galactic disk. Comparing the inflow rate to the star formation rate will provide a better timeline of the evolution of normal star-forming galaxies, and explain how galactic disks continue to grow over very long timescales that span billions of years.